Good morning, grade 12s. It is Wednesday morning, May the 27th, and we're getting rapidly approaching the end of our unit on electricity. Again, by Friday, we want to be having a test. And if you noticed, later on today, Wednesday at around 11 o'clock, I've opened up a Zoom for a class tutorial so you can come and ask your questions on this unit. I know I've had a couple of questions in the last little while that I haven't done videos to answer, but that would be a chance for you to come. If you've had questions in the last little while, come ask your questions. We'll cover some things. I'll be able to use the whiteboard app that is within Zoom in order to be able to show you some work on how to do some of the questions, and maybe that will answer some of your questions. So join us for that. Before we get going into what we want to talk about today, I want to start you off with a verse of the day, and today it comes from Psalm 63 and it's verses 2 to 5, where it says, "I have seen you in the sanctuary and beheld your power and your glory. Because your love is better than life, my lips will glorify you. I will praise you as long as I live, and in your name I will lift up my hands. I will be fully satisfied as with the richest of foods. With singing lips, my mouth will praise you." So just a reminder to behold the power and glory of our Lord Jesus, to allow your lips to glorify him throughout the day today, and be satisfied with what he has blessed you with. All right, today we're going to be talking about Transformers. Hope you liked the little song intro. And but what allows us to use transformers is the idea of alternating current, and how alternating current and Faraday's ring can allow us to make changes to induce a current. And so we're going to start today by looking at what alternating current allows us to do. And I've got a little problem here for you. It says calculate the percentage of electric power wasted as heat in a transmission line if 10 kilowatts is transmitted along a cable with a resistance of 1 ohm at an electric potential of 200 volts. All right, so when we transmit electrical energy through power lines, there's a resistance in those power lines, and electrical energy will be dissipated as heat. The entire cable is a resistor, and it will generate heat, and that electrical energy will be lost to heat and won't be able to make it to our homes and the resistors that we want to power. And so when we look at an example like this, and I'm just going to grab a whiteboard marker. There we go. And so we're going to look at this, and if we want to do this, we're going to calculate the current that is flowing through this situation first, remembering that power equals current times voltage. We're given power, voltage, and resistance, but we're going to not look at the resistance for now. We're going to look at what's the current flowing through here. And so again, P equals IV, and if we solve for I, we're going I equals power over potential difference. 10 kilowatts is 10,000 watts over our potential difference of 200 volts. That gives us a current flowing through of 50 amps. That's a really terrible 5. Let's try that again. 50 amps. All right. Now, if I take that 50 amps and I run it through my 1 ohm resistor, what happens? Well, again, we want to look at what power then is being dissipated by the 1 ohm cable. And so now we're going to go power equals, and now we have resistance and current. We have a current of 50 amps flowing through a 1 ohm resistor. What electrical energy is being used up by that? So we're going to go I squared R as our formula. And if we do that, we're going to get 50 amps squared times our 1 ohm resistor, and that power is going to be 2,500 watts, or 2.5 kilowatts. Okay, so we started with wanting to transmit 10,000 watts, or 10 kilowatts, and 2,500 watts is being wasted to heat along the transmission line. That's 25%. right? That is not very efficient. If we were transmitting electrical energy at 200 volts, along the way we would lose 25% to heat in the cable, which is a resistor. That's not a good way to, not a good business model to lose 25% of what you want to transmit. But we're going to redo this calculation. What if instead of 200 volts, we were to up that to 2000 volts? Okay? So let's just do 10 times greater. Okay? If I up that to 2000, now I'm going to change my markers here so that we can see what changes we're making. Because it's the same formulas. We're going to change this voltage here to 2000 volts. Okay, if I do that, then the current here is no longer 50 amps, it is 5 amps. And if I go over to here and I change this 50 to 5 amps, instead of 2,500 watts being lost, we will lose 25 watts. Okay, so now, started with 10,000 watts, 25 watts is being lost to heat. Well, that's now a 0.25%, 0.25%. So by simply upping the potential difference from 200 volts to 2000 volts, we went from losing 25% to heat to losing 0.25% to heat. And if we could make this voltage go even higher, then we could lose even less in our transmission. So what we want to say here is the higher the voltage, the higher the potential difference that we can use to move energy from one place to another, the less we're going to lose in the transmission. And so we want to make that go as high as possible. And to do that, in order to change the potential difference, we're going to use a transformer. Now, a transformer is simply Faraday's ring. So we're going to go to the other board and we're going to look at transformers and some of the relationships in transformers that allow us to step up the voltage and step down the voltage potential difference as required using transformers. Okay, so on the board behind me now, we've drawn a transformer. And in a transformer, we have an input side and an output side. So what this might look like is, on this side, we're sitting at a Manitoba Hydro generating station up in northern Manitoba. We've got a generator on this side creating an alternating current. And on this side, this will be going towards a substation, a transformer substation, where we'd have a number of transformers along the way that we'll look at stepping up the transmission, the potential difference for transmission, and then eventually we'd step it back down as we get the electrical energy to our homes. All right, so we have on this side a small number of windings. Okay, we only have 3 wraps around this side, and on this side we have considerably more windings around our transformer. And what it has found out is that the number of windings is directly proportional to the potential difference output. All right, and it's a very simple relationship. The number of windings on the primary side, we'll call that 1, N is for number of windings, and 1 would be primary. The ratio of windings to the secondary side, so the ratio of windings to the first side to the second side, is equal to the ratio of the potential differences. All right, so we get this formula here where the ratio between the number of windings has to equal the ratio between the potential differences. And so if we have this scenario where we have less windings on the input side and more windings on the output side, we have what's called a step-up transformer. A step-up transformer is a transformer that makes low voltage go into higher voltage, right? The direct proportion between the ratio of the number of windings, the number of wraparounds the transformer versus the potential difference that it puts out. All right, so that's how that works. And then if we look at the power output, now in this world, in this physics class world, we're going to consider our transformers to be what are called ideal transformers. And in an ideal transformer, there's no power loss within the transformer. All right, so they're perfectly efficient and there's no power loss. Not the case in the real world necessarily, but it's going to be close enough and good enough for us to consider that the power on the input side, we'll call that 1 for primary, has to equal the power on the output side, which is 2. All right, and of course, our formula here is IV, so I1 V1 has to equal to I2 V2. Okay? And if we put the currents onto one side and the potential differences onto the other side, we'll get another ratio that is I1 over I2 equals V2 over V1. All right, and of course that can be flipped so that you'll get V1 over V2 equals I2 over I1. But in a sense, we get another ratio here. The proportion for the currents is inversely proportional to potential difference. And we saw that in our example we did there. When we upped to the potential difference, the current dropped. All right, so same thing happens here. What this does is it gives us one formula. It's got a 3-part formula similar to sine law. If you remember what sine law is, that looks like this, where we have N1 over V2, or sorry, N1 over N2 equals V1 over V2, which equals I2 over I1. And so this becomes our transformer formula, where the ratio to the number of windings is directly proportional to the potential difference, which is inversely proportional to the current. Okay, which simply means that the more windings gives us more voltage gives us less current. Okay, and what this allows us to do again is it allows us to transmit electrical energy from where we generate it to where we need it efficiently. Because we don't transmit or we don't generate electricity in the urban centers where we need them. Think of all of the generating stations you can think of anywhere in the world. Okay, whether we're setting up windmills or whether we're setting up hydroelectric dams or whether we're setting up nuclear reactors, they're not done near city centers. Right? Manitoba hydro dams are all way up north on the rivers in northern Manitoba. The windmills are set up on farmers' fields in southern Manitoba, again, way far away from the urban centers where they're used. If you're setting up a nuclear reactor, they are set up, again, far away from city centers, just because that's where the impact on the community and the impact on the environment is lessened by that. All right, and so if we can then generate them there, at whatever potential difference we can generate them, we can use a transformer to step up the potential difference, which lowers the current, which lowers the amount of energy lost in transmission. We transmit it to where we want, to our towns, to our cities. We step it down, we transmit it to our houses, we step it down until we finally get it into our houses where we have a 240 volt line coming into our house, which then again gets stepped down into 120 volts so that we can run the appliances that we have. All right. So that's the way the theory works. Let's do a quick example, and then I'm going to photocopy you some pictures and an assignment that you will find on Connect for you to do dealing with this. So here's our example. The example says a transformer is designed to operate a 12-volt door chime from a 120-volt supply. If the transformer has 800 turns on the primary coil and the door chime draws 1.5 amps of current, find A, the number of turns on the secondary coil, and B, the current supplied by the primary coil. So again, in a transformer, we have a primary side and a secondary side. We have a primary coil with a number of windings. We have a secondary side with a number of windings. When I talk windings, in a question I'll talk turns. It's how many times has the wire been wrapped around on that primary and secondary sides. So to answer this question, we just need to know what we've got here. And the primary side is 120 volts, that's your primary potential difference, and we have 800 turns on the primary side. We're also told that we have a secondary potential difference of 12 volts, right? Now, if we think of our formula, which we just had, right, N1 over N2 equals V1 over V2, this gives us 3 of those 4 parts. What I would do in solving for part A is I would write the formula as N2 over N1 equals V2 over V1, which is exactly inverse from what we wrote on the board over there, which is totally fine. If you have 2 fractions that are equal, 2 ratios that are equal, you can flip them both over and it's still true. And so we're going to have this, and the reason I'm doing this is because I want to solve for N2, and having my unknown in the numerator is much easier to solve for. And so what this gives us then is it gives us N2 over 800 equals to 12 divided by 120. And we can see that there will be 80 turns. So N2 would equal to 80 turns on the secondary side. Right? Again, because it's a step down transformer, we're going from 120 volts to 12 volts, we need less windings on the secondary side than we had on our primary side. And again, I don't recommend you doing this, but if you were to pull apart your doorbell on your house, there would be a little transformer in there with some windings, and don't do that. Don't pull apart your home's doorbell. Your parents may not be happy with that. All right, to do part B, we do the same calculation, except now we're using potential difference and current. And again, the formula that I would use for part B would be I1 over I2 equals to V2 over V1. And again, simply because I1 is what we're looking for, the current in the primary coil. And by putting in the numerator, it's just easier to solve for. If you put your numbers in, if you put your 1.5 amps in for current here, your 12 and your 120 volts for V2 and V1, you will find that I1 would equal to 0.15 amps. Okay, and I'm sure you can do that calculation. You can put those numbers in for the appropriate parts. 1.5 volts, 12 volts, 1.5 amps, 12 volts, 120 volts, and you can get that answer. And so again, we can see that the primary side that had the higher potential difference has the lower current. Secondary side had a lower potential difference, but a higher current. And that's how transformers work. And so you're going to get an assignment, a handout that you'll find on Connect, as well as I'm going to give you a bit of a diagram of and a little bit of information on distribution of electrical energy that will explain and show you in pictures a little bit more of what we've talked about in terms of distributing energy from where it's generated to where we need it. Again, if you have questions, make sure you ask. Again, if you're watching this in the morning, on Wednesday morning, we do have a class Zoom at 11 o'clock on Wednesday where you will have a chance to ask questions and we'll go over some things there. So have a great day and we'll see you tomorrow.